Hello everyone, welcome for today's quantum space time seminar. Today we have Prahar Mitra from University of Cambridge, and he's going to tell us about shadows and soft exchange in celestial CFT. Over to you, Prahar.
Hello, thank you everyone, and thank you to the organizers for inviting me back to TIFR and giving me the opportunity to talk about this recent work. So I'm going to apologize for a bit. I gave this talk at a Celestial Amplitudes conference just a couple of weeks ago. So if anyone was there in the audience was also there at that conference, I really apologize. This is going to be more or less that same talk. So what I'm going to talk about today is based on a paper that recently came out in September by work with Daniel Kapitz. And I'll just mention right away that there's a whole bunch of very closely related work on this exact idea. So I'm just going to list all of them right now. And I won't mention any more literature for the rest of my talk. The one thing I will mention is that all of these talks have been for 4 dimensions. And what I'm going to talk about today is general dimensions. So in some sense, it's a generalization of all of these results. And the idea is to sort of have some sort of unifying principle that you can use to construct these soft actions. Okay. So the goal is the following. So the idea is about celestial CFT. So celestial CFT is the name that is given to a CFT that is dual to quantum gravity in flat space-time. If such a dual actually exists, that CFT is called celestial CFT. The reason we call it a celestial CFT is that it has conformal invariance. So it has charges that generate conformal symmetry, but it really doesn't have any of the other properties that we associate with CFTs. So it's not even clear right now if what sort of representations appear. They're likely not the standard highest weight representations. We don't know anything about unitarity. Even the OPE structure is not extremely well known, though we are slowly uncovering things step by step. But the structure is very different. So that's why it's been given its own special name called celestial CFT. So what we'll do is, of course, the grand goal would be to do something like ADS-CFT, where we have an explicit action on the boundary, and that's dual to some explicit theory in the bulk. And then we can try and compute things on both sides and match things. That's very difficult to do because we don't yet have any sort of top-down construction of flat holography. If we could find some asymptotically flat geometry hidden inside string theory, that would probably be the best way to go. People are looking at that, but we haven't really found anything yet. So we're using a more of a bottom-up approach. So we try to construct the action using symmetries to the extent that we can. So what I'll do today is I'll construct at least part of the action. Of course, the action is complicated, contains a whole bunch of fields. So I'm going to construct just a small part of it, and it's the part that reproduces soft exchange and soft theorems in all gauge and gravitational theories. Sorry, just a minute. Okay. And it's going to be done in all dimensions. So let me briefly mention a couple of things about this. Why do I want to, I've sort of mentioned to you, why do I want to go above 4 dimensions? So 4 dimensions, d equal to 4 is a bit special because the dual CFT for 4-dimensional bulk gravitational theories is a 2D CFT. The duality works a bit differently compared to ADS-CFT. It's 2 dimensions lower. So it's a 2D CFT. And as we all know, 2D CFTs are very special. There's enhancement of various symmetries. Almost everything is an infinite dimensional CFT, infinite dimensional symmetry. So there's lots and lots of constraints that you can impose on the structure of your CFT. And that's good, obviously. In one sense, it's very good because it enforces a lot of constraints, which you can hope to solve. But the problem with that is that because it's so special, it hides certain general features that one might expect for celestial CFTs. And we hope that by studying the general dimension structure, after stripping away all of these special properties, we can then try and understand what are some of the more general, more basic features that we should expect for any celestial system.
So Prahar, would an analogy be that ADS3 has certain special properties, for instance,
Exactly.
in the algebra? Is that a fair analogy?
Absolutely, it is. Yes, indeed, it's more than a fair analogy. There is even an exact relationship between them, where you can take, you can think of four-dimensional Minkowski spacetime as a foliation of 3D ADS slices, and then it's 3D Euclidean ADS slices, and then you can do ADS3 CFT2 on each of those slices. So this is actually this is a very explicit way of sort of utilizing ADS CFT and trying to understand flat holography through this method, which was originally started in quite early, actually, in 2003 by De Boer and Suludikin. Okay. Though you might ask, so if I'm interested in soft exchange is usually trivial in higher dimensions because there are no infrared divergences. That is true, but you still have contributions from soft photons if I don't take the energy cutoff all the way down to zero. If I take the energy cutoff, the infrared cutoff all the way down to zero, then the contribution of soft photons is trivial. But if I don't do that, you still get some non-trivial contributions. And that's actually a pretty physical restriction because in any experiment, for instance, any device will have a low energy threshold below which it actually can't do any measurements. It can't measure any photons below a certain energy threshold. And then you'll expect that you have to integrate out all the modes with energies below than the energy threshold. And in that case, the physics of all the photons below that energy threshold will be governed by the action that I will discuss today. So even though there are no infrared divergences, there's studying soft exchange in higher dimensions is still a thing of interest. And of course, soft theorems is something that exists in any dimension. That doesn't really care about infrared divergences or not. Okay, so for many reasons, I hope I've convinced you that it's nice to study D greater than or equal to 4. D equal to 3 is another special case, which I'm hoping to look at some point. It has several other new features, but I won't discuss this in the talk today. Okay, so let me just briefly tell you the idea, and then we'll get into the specifics later in the talk. So what we'll first do is I'll have an IR cutoff mu, and this mu cutoff is just going to be used to regulate infrared divergences. So of course, in greater than 4 dimensions, you don't really need to introduce it, but I'm going to discuss all dimensions in just a single sort of formalism. So I'm just going to introduce it to keep track of everything. And then the scale lambda, which is the thing that separates what we want to call soft photons and hard radiation. So you can think of this as the energy threshold for your device. If you want to be a bit experimental, but if you want to just think of it theoretically, it's just a delineation between what we refer to as soft modes and hard modes. And I'm going to assume that mu is obviously less than lambda, but that both of these energy scales are much smaller than the typical energy scale of the scattering that you're looking at. So it's much smaller than the center of mass energy, say S, a square root S. Okay. Okay, so let's look at briefly how this is going to work. So here on the left-hand side, I have an amplitude with the energy cutoff mu. What I mean by this lower cutoff mu is that on the right-hand side, when I do the path integral over all the fields in the theory, I'm going to put a low energy cutoff mu in momentum space to do the path integral. Okay, next, I'm just going to separate out the fields, all the fields into a soft field and a hard field. The soft fields are, as I mentioned before, they have energies between mu and lambda, and the hard fields have energy greater than lambda. That's what I mean by this. This is something that was also done by in various papers by Ashok and Biswajit Sahu and Alok Ladha, where they use this very interesting decomposition of fields into soft and hard to derive these really complicated and beautiful soft theorems in all dimensions, to all orders in the soft expansion. Really, I think it's a beautiful work. Okay, so we do that, and then this is the first place where it's sort of assumption comes in, but it's a pretty well motivated assumption, and the assumption is that these operators OI, which you're inserting in an S matrix, also factorize into a soft piece and a hard piece. Now, we can motivate this in hindsight, because as we will just see in a few seconds, is that it ends up giving you a soft hard factorization of the S matrix. And a soft hard factorization of the S matrices is something that has been computed and known for a very long time using independent methods. But also, it's also something that we know has to be there from a covariant phase space analysis, which is something a lot of people have been working on recently in this analysis. And it's sort of there's a lot of hints and motivations from that point of view that operators OI factorize into these two pieces. So unless I spend a lot of time explaining covariant phase space, I think that's a whole other talk. I'm just going to take this as an assumption for now.
Sorry, and these operators, Prahar, are they on shell?
They're all on shell. I'm going to give you all the details, explicit details soon, but they're all on shell. So these are just the creation annihilation. So think of them as A, out, momentum. So they just, or A in, P dagger, the operators that you insert, the in and out creation annihilation operator.
So this thing is the S matrix?
This is the S matrix on the left-hand side.
Okay, thank you.
It's not a correlation function. So LSC theorem has been used already to extract out appropriate poles, and it's just the S matrix. Okay, so I'm just going to assume this. And let's just see what that gives us if I just make this assumption. So what I'm now going to do is just integrate out all the hard modes. So again, let's go through that step by step. It's relatively easy. So this d phi is separated out into a path integral over the hard modes and a path integral over the soft modes. The operators UI depend only on the soft modes, so they factor out. S bulk, of course, has some dependence on the soft modes. So when I integrate out all the hard modes, I'm going to get an effective correlation function with now a cutoff lambda. Remember, because I'm integrating out over all the modes from mu to lambda. And then I'm going to get an effective action of for just the soft modes.
Sorry, Prahar, just to understand. So the field O, the field phi, O could be a composite operator of the fields phi. It could be like phi square.
Yes, it could be. Like if it was a pion, it could be QQ bar, for example.
Okay. So, and then this factorization, it's the statement that there's another operator made only of the lighter phis, and another operator and an operator made only of the heavier phis, but no cross terms.
No cross terms, exactly.
And if you just substituted in the operator, that wouldn't be true. But somehow that's like it flows down to that or something like that. Yeah,
it flows down. I mean, it gives us the soft hard factorization here. So that's one motivation for that to be true. And it also sort of follows from a semi-classical analysis that you do using covariant phase space, which, if I had to go through that, that would be a separate talk, but it does follow at least at a semi-classical level that such a factorization exists for all of these operators.
Yeah, and I don't at all want you to go through the whole thing, but just if I just substituted phi, O is phi, then there would be some, in the substitution, there would be some cross terms, right? Soft, hard.
In the substitution, there would be. But then when you extract out all the poles following the LSC theorem, the claim is that after you do all of that process, then it would factorize.
Thank you.
Yeah.
And the same would be true for the measure?
Again, assumption. The measure is a bit easier to see because if you look at how the measure is even defined, at least in naively how it's defined is that we define it in momentum space. So what is defined over here, we can go to momentum space, d phi p, and this original measure is defined as by taking a low energy cutoff mu. So now we can simply define this measure as being equal to the integration from mu to lambda, d phi p, and then from lambda to, again, goes up all the way to infinity. Maybe even you need a UV cutoff. I'm not caring about UV cutoffs and all. Let's assume the theory has been renormalized already. And this is this thing is what's being called d phi h, and then this thing is d phi s. So the factorization of the measure is a bit more motivated, but again, maybe there's complications and I'm not going to worry about them.
So Prahar, one question.
Yeah.
These operators form a vector space, right?
Yes.
Then is there a preferred basis here which obeys this property? Because you can just
very good
linear combinations of these. where the factorization will not hold by construction.
You are
right?
absolutely correct. There is a preferred basis. That's a very good question. There is precisely a preferred basis. It's the standard basis of when we do perturbation theory. It's literally this holds for the operators A out P. This factorization does not hold for the Faddeev-Coolidge operators, where you put in a whole bunch of you put in a whole bunch of extra soft modes,
Right.
surrounded by photons, integrated over a bunch of things. Then it's no longer factorization, but even then it's almost a factorization, because then you can think of the Faddeev-Coolidge operators as Ui phi s Oi h, and then you're integrating over some d to z, where all of this depends on z. I'll explain what zz bar are later. So this phi s also depends on zz bar. So in that case, it's not a trivial factorization, but it's still a linear combination of factorized operators.
Okay, thanks.
Yeah, I think that's a very, I should have mentioned that. That's a good question. So this factorization holds for the standard basis of scattering amplitudes that we're all familiar with, that we work with. Indeed, also the soft hard factorization is also only true for that basis. Otherwise, you have to sum over. That's what I meant here. Okay, so if I just, yeah.
Can I ask? I mean, I can compute scattering amplitudes in some strongly coupled theory like QCD, right?
Yes, you can compute, but in a strongly coupled theory, so when you say scattering amplitude, you have to look at asymptotic states. So yeah, you can work with strongly coupled theories, but the asymptotic states are still pions.
Right.
And then pions have this soft hard factorization.
Okay. Okay, thanks.
Could you please explain again why the S bulk, in the S bulk, there would be no interaction terms between the S phi h and the phi s?
No, there'll definitely be. There'll definitely be. But once I integrate over phi h, then I'm just going to get an effective action just for the soft modes. At this point, I'm not making any claim about the relationship between phi s and phi h. There will definitely be interaction terms in here. But after I integrate out all the hard modes, then I'm just going to get some term which is an effective action of the soft modes, and then everything else. Indeed, this exact form of the action has been worked out on a case-by-case basis very explicitly in Ashok Sen's work, where he tries to derive the soft theorem. So in one paper, he derived this to all orders, the soft graviton theorem. There he has to understand precisely the interaction between the soft graviton and the hard gravitons. And then there's this complicated action which he writes down, which if you want an explicit form of that, you can look at Ashok Sen's book. Okay. The important thing is that we won't need any of that. What is nice is that what I'm going to do, let me just say it right now, what I'm going to do, I'm going to, this is just a brief explanation for the method. Then I'm going to just focus on this S soft. I don't even care where it's coming from. My goal will be to use symmetries to fix what to fix the structure of S soft. And as we'll see, it's sort of more or less uniquely fixed. And we'll see that symmetries completely give us the full soft hard factorization without having any knowledge about where this S soft actually came from. Okay. Okay. So anyway, okay. So we see that there's by assuming that these operators themselves factorize in some way. Again, I think it is relatively well motivated. You find that the S matrix itself has a soft hard factorization. Now, the soft hard factorization of the S matrix is a well-known fact. It's been derived very explicitly in an exceptionally long paper by Matthew Schwartz, where he used various. Anyway, it's been derived explicitly to all orders in perturbation theory. You know, he resummed all loop orders, and you can actually show that you end up getting something that precisely of this form, and this soft factor over here is at least in his notation is called e to the minus gamma. So I'm going to use the same notation, and this gamma is related to the cusp anomalous dimension of the theory. Indeed, this UIs are going to be Wilson lines, and so this will just be a correlation function of Wilson lines. Again, I'll write all of these out explicitly. So this is another very simple and sort of two-line way to motivate the soft hard expansion of the S matrix. Now, so far, I assume that all of these operators, OIs, that was appearing in the S matrix are all radiative modes. So they're pions, radiative pions, and whatnot. But we know that there are other types of S matrices we can consider, and these are S matrices which themselves have soft external photons in them. And so I can additionally also consider S matrices with external soft photons. Let's say some SIs. These could be external soft photons, gravitons, and all sorts of other soft operators that we now understand. And there are these whole class of soft theorems, which tell us that whenever you insert a soft operator in your S matrix, so if I have an external soft particle, that's what this represents on the left-hand side of this equation, then the amplitude also factorizes. And it factorizes into this form with curly J1 and curly Jm. These are called soft factors. So if I put this result together with the result that I've derived here, at the end of the day, we'll find that if I just focus on the soft part of this entire discussion, you might have a bunch of external soft particles, SIs. You have these other sets of soft operators, UIs. So they're two independent soft modes, the SIs and the UIs. And then I compute this correlation function with respect to some soft action. And if everything is correct, it should reproduce precisely this term on the right-hand side. So this is what we know should happen. This is just from basic S matrix theory. We know that this is the type of structure that we expect. Okay, so what I'll now do in the rest of this talk is after giving certain explicit definitions of all of these quantities that I've spoken about vaguely here, is that I'll show that this boxed identity follows purely from symmetries. You don't actually need to do any complicated Feynman diagram calculations to derive this, this equation. Okay, any questions? That's the end of my introduction.
Sorry, and if I was just computing S matrices using Feynman diagrams,
yeah,
the soft part would be the contribution of all the soft fields running in all the Feynman diagrams?
Yes, in the loop. So I'll have a diagram. I'll show a diagram later. So the soft gamma comes from diagrams of this type. When you have soft operators, so orange line corresponds to soft, and a soft photon that is running in the loops. And so these things contribute to e to the minus gamma. And then if I have a soft operator as an external particle, then these things contribute to ji, these soft mode.
And this the soft part of the operator, is that largely independent of the details of the hard part of the amplitude?
More or less. So it depends on the momenta of the particles. Actually, well, it depends on the momenta and it depends on the charges of the particles. And as we see, and we have discussed before, it also, to a certain extent, depends on whether the particle is in an incoming particle or an outgoing particle. And that distinction is sort of crucial for some.
Thank you.
Reasons. Yeah.
So, Prahar, one question. So, yeah, if the mass of the hard particle, the external hard particle, is greater than mu,
yes,
then I don't quite see, maybe you will say this, but I don't, what is the soft piece of that operator then? It looks like it's trivial that there is no soft. Because
no, not soft piece of that operator, but the point is that if the operator is charged, so for example, think of an electron. If the operator is charged, then a free electron doesn't exist, because as long as you have a massless photon, you have long range interactions.
Okay.
So the correct state when you want to describe an electron is always going to be the electron itself, which is just the hard part. And then it's going to be coupled to some sort of surrounded by a cloud of soft photons.
Yeah.
And that cloud of soft photons is the thing that's the
U. Okay.
That's the UI. Again, which we'll show is related to some Wilson lines by symmetry, but this has also been known for a long time that it's related to Wilson lines by work of Matthew Schwartz, where he has this exact factorization formula in terms of some sets of Wilson lines.
Thanks.
Okay. Okay, good. So this is, I've been very vague. Now let's be precise. So in the rest of this talk, in the review, I'm going to make everything explicit, very precise. And then in section 2, I'm going to tell you how we use symmetries to derive the action. It's basically using the standard ideas from spontaneous symmetry breaking. So that part shouldn't really be, if you have studied spontaneous symmetry breaking, it should be sort of trivial to follow, I hope. And I'll do section 1 and 2 because of the simplicity, and it's a talk just for abelian gauge theories, because it's the simplest possible example that I can show in a talk and not confuse people. But in section 3, I'll just show that it can be done for gravity as well. It can be done for non-abelian gauge theories as well. I'll just flash a bunch of formulas. Okay, so let's start. So the first thing, I'm just going to introduce some new notation, because this will be very useful, and it is very useful in the study of celestial CFTs. So I'm going to parameterize momenta in this way. So it's easy to check. You guys can go and check it. So here q hat squared and n squared are null vectors. And you can check that this parameterization precisely gives us p squared equal to minus m squared. So it's a nice parameterization. We'll also need, because we want to discuss, incoming and outgoing momenta, we just identify with the sign of omega, that's it. So if omega is positive, it's outgoing, and if omega is negative, it's incoming. I'm not doing any analytic continuation with crossing symmetry or anything of that sort, just positive or negative, just a convention, just notation. We'll also need the polarizations for gravitons and photons. And the polarizations are very simple. So in D plus 2 dimensions, massless particles transform according to the little group SOD. And so a photon is a vector of SOD. So it has 1 to D components. I should have mentioned what this A is. This XA is just X1, XD. So it's just an index that runs from 1 to D. And so a photon has D polarizations in D dimensions, and that's what this A is. So as you can see, there are precisely D polarizations. And a graviton transforms under the symmetric traceless representation of SOD, and that's given by this formula right here. And you can check that it satisfies all the nice properties of polarizations that we expect. In particular, we have epsilon A dot epsilon B. So these are the standard linear polarizations. Okay. And these are the operators of the definitions of the operators O that I was alluding to previously. It's very simple. It's literally just the in and out creation annihilation operators. So if omega is positive, then it's just an outgoing, it inserts an outgoing state. And if omega is negative, then it inserts the CPT conjugate of the incoming state with momentum P. Okay. Okay, these are all just definitions. So with
sorry, I missed. What is X again, please?
Oh, X is just the parameter that's appearing in the, I'm going to parameterize my momentum in this way. So it's appearing in X.
And what is that parameter?
It's just a vector. So it's a bunch of X1, XT, X, and I've defined everything explicitly here.
Okay.
So Q mu is defined as this thing. And X squared, by X squared, I mean XA. So it's just a vector in D dimensions.
Okay.
It is actually explicitly just a Cartesian coordinates it's the stereographic coordinates on the D dimensional sphere on SD.
And so far, you don't have any cutoff on omega, right?
I don't have any cutoff on omega, but indeed the cutoffs that I was mentioning to you previously was going to be on omega. So what I'm going to mean by soft is mu greater than absolute value of omega greater than lambda. And what I mean by hard is going to be omega greater than lambda.
So are you saying that the momentum is dependent on some vector? This X is X sort of the position vector or something? No.
No, the momentum is constrained, right? Momentum is p squared equal to minus m squared. So in D plus 2 dimension, it depends on D plus 1 independent variables. And you can choose to parameterize those variables however you want.
Okay.
Right?
Fine.
I think roughly speaking, it's the direction in which the particle is going.
Right.
Yeah, actually that's true in the massless case. When m is equal to 0, you can think of x as simply the direction of the vector, and then omega is the energy. Direction, so because on the sphere, you can introduce stereographic coordinates. So you can parameterize your sphere with coordinates x, and then every point is labeled by a value x. And then that x in the massless case is precisely the direction of the moment. Yeah. Any other questions? It's just a chosen parameterization. Again, you might be asking, this is a weird thing. Why should I do this? But the next slide will explain it to you.
Okay, fine. Go ahead.
Okay, so using this notation, again, at this point, it's purely notation. I've not done anything fancy. It's now clear that I can write an S matrix in this way. So where the sign of omega tells you whether it's an incoming particle or an outgoing particle. And then there's omega 1 x1, which tells you, which, as we have discussed in the previous slide, parameterize the exact momentum. So this is just simply a rewriting of O1, P1, ON, Pn. Okay, just notation, which I'm just going to, for simplicity, I'm going to drop all omega i's, xi's, and just write it as O1 to ON, unless we'll need it explicitly. Okay, this is the reason this is nice, because up to a generalized Mellin transform, a formula which I will just tell you, this S matrix in these coordinates transforms precisely as a correlation function of n conformal primary operators. And here, in making the statement, I'm exploiting the isomorphism between the Lorentz group, which is SO 1, D plus 1, and the conformal group on Euclidean D dimensions. So these two groups are completely isomorphic, and therefore we know the S matrix transforms in some way under the Lorentz group. So it's clear, because of the isomorphism, if I can find a nice coordinate system, then I should be able to write everything in a way that makes the conformal symmetry manifest. And in holography, that's something you really want to do. I want to write everything on the bulk in terms of some correlation function of highest weight local operators in a CFT. And we know from various studies in a CFT that we want to make the conformal group manifest. So that's what these things do for you. Yeah.
Sorry, I mean, this is true also for massive states, or only
also for massive states. Let me now tell you the formula. Here's the formula. Here's what you have to do to go from the omega I xi basis to the delta x basis, delta being the scaling dimension. This k delta is the bulk to boundary propagator in ADS. And so if you do perform this integral, for m greater than 0, this is for the massive scalar.
So the previous construction, I mean, one can think for at least for massless states as some sort of an embedding space construction, right?
Exactly. So for massless states, it's a much simpler. Maybe I should just show you all the formulas straight away. Here it is for massless particles. The transformation for massless particles is exceptionally simple. It's local in X, firstly. Right. It's local in X. It doesn't change X at all. It just rescales omega. And this should be obvious from the embedding space formalism.
So is the meaning of this equation for massive guy is that, naturally it would live on some hyperboloid, right? Yeah. Because p square is equal to m square or minus m squared. And then you kind of think of that bulk operator as an integrated boundary operator in this way. It's
exactly that. That's why these coordinates are chosen, actually. To the eagle-eyed, you will know that. So p squared equal to minus m squared defines for your Euclidean ADS. And this coordinate system that I've introduced here are the Poincaré coordinates in ADS, with this m over omega is the radial coordinate z. Right. So these are the Poincaré coordinates. And so essentially taking z to 0 corresponds to moving to the boundary. And we know in ADS how to map a bulk operator to a boundary operator. You just use the bulk to boundary propagator. And that's what's been done here. So you use the bulk to boundary propagator to map an operator that's living in the bulk of ADS to the boundary, which depends just on a point X. And then there's an extra delta, which tells you the scaling dimension of it.
So if you want to prepare one massive state with a particular momentum, you would have to smear it.
You have to smear it over all delta. This is the reason for that is because in ADS
or all X, I mean, or X, I mean, X,
sorry,
delta also, because you want to prepare something with fixed omega, but in addition to that also X, right? You would have to smear.
Also X, again, it's a matter of basis choice, because this is just a basis transfer. So if you want to construct a particle with a given momentum, where the momentum is diagonalized, then you have to, of course, smear over both delta and X. But the whole point of the celestial CFT is that I don't want to make translation symmetry manifest. I want to make the Lorentz symmetry manifest. So I want to work in a basis which diagonalize the angular momentum generators. Right. And if I want to work in that basis, then I don't need to smear over X at all. But delta has to be smeared over. This is something it's not usually done in ADS. Why? That's because the bulk fields satisfy equations of motion, usually, which picks out a particular value of delta. But here the bulk fields don't satisfy any such equation. So you actually have to sum over all possible delta to reproduce a generic field in the bulk.
No, so sorry. I mean, just to kind of reiterate my question here. Yeah, I mean, you're right. That's what you would like to do, that to make the you want it to be local in X and everything. But let's say you want to at some point get scattering the usual scattering amplitude of massive particles.
Yes.
Then you would have a fixed momentum, right? You want it as a function of matrix variables or some momentum variables. Yes. And for that you would need to take this local correlation function in on the boundary CFT, and then and smear over X to produce a fixed momentum.
Absolutely.
Also, right?
I can write down the formula for you if you want. So
it's just inverse of this, I guess.
It's literally the inverse of this, and I can show you the formula if you want to look at it. It's T/2 plus minus I infinity, D/2 plus I infinity, D delta, dd y. All right, let me remember this. K d minus delta m over omega y x or delta y. So that's what you have to do. So you have to smear over y and as well as over delta. And notice that the smearing in delta is over the principal series axis. So this actually suggests that the correct set of operators that show up in celestial CFTs are the highest weights in the principal series, not on the real axis.
Right.
This is a bit of an open question, actually. Anyway, I won't make any more comment on that. Anyway, so this is what you will have to do. You have to smear in both y. So indeed, you are correct that in the massive case, we should not think of these operators as local operators with respect to X, because you have to do this sort of smearing. And we'll see a result that will sort of reinforce this in a bit. However, in the massless case, they are local, because as you see in the massless case, the smearing doesn't touch X at all. So it doesn't actually affect X. So in the massless case, these operators omega X are local with respect to this variable X. And again, we'll see this. Okay, let me go.
Prahar, can I ask something? It's a very nice question. So, if I, let's say, parameterize massive particle momenta, let's say I introduce one more zeroth component such that it is same as the mass, okay? And then rewrite it as a one higher dimensional massless particle. And your formulas looks like very general in D dimension. Can I not still use the massless formalism for that?
Well, just adding momentum won't be enough because they transform under different little groups.
Not. So P square is equal to M square is a formula. What I do is that I just introduce another coordinate P0 is equal to M square, such that now the new P tilde square is 0.
Yes.
And then it's like a one higher dimensional representation of massless representation. And can I then use your massless representation to do?
But M and P0 are not exactly the same. P0 is like a momentum and M is a constant. I guess that's the difference.
I think maybe he's saying you take a higher dimensional momenta and you just focus on the set of momenta such that P0 is forced to be M squared.
You would use this kind of trick sometime to do scattering amplitude, right?
I don't know that could be possible. The thing that bothers me about this is that the momentum is not the only thing that defines a particle. It's the little group, which is completely different based on which dimension I'm sitting in, whether it's massless or massive. So unless you can also match that, might be possible. I haven't thought about it.
Okay.
Okay. So I just wanted to show you that explain to you why this is an important thing to do, because this is the relationship between celestial CFTs and scattering amplitudes. We have a set of correlation functions of some highest weight operators with dimensions delta. The deltas live perhaps on the principal series. And then you have to do some smearing which I've shown here explicitly for you guys here. You have to do the sum spearing in order to reproduce the momentum space scattering amplitudes. So this is how the conjectured, the holographic duality, this is the dictionary in some sense. Okay, now that being said, I'm not going to work in the Mellin basis. Because again, it's just an extra factor of the smearing that we have to worry about, and the formulas that at least I'm going to present are much nicer in the omega basis anyway. So I'm just going to stick to the omega basis, and I'm not going to bother with the Mellin transforms.
Sorry, why are you calling this a Mellin transform?
Oh, it's almost a Mellin transform with this extra kernel. This sort of type of thing is a Mellin transform. So Mellin transform is integral 0 to infinity d omega to the s minus 1 of f of omega is f star of s. This is it. And it's called a generalized Mellin transform because you have this extra kernel. But in the massive case, it literally becomes a Mellin transform. In the massless case. So this is actually exactly Mellin transform.
Okay. So I mean, I should not think of it as a very parallel to the perhaps very closely related to the Mellin transform that they consider in CFT, right? It's just mathematically it's a Mellin transform.
It's just a mathematically Mellin transform. In a CFT, they're doing a Mellin transform on the STU parameters, and they're doing it on the amplitude without the delta function, just the amplitude.
Right.
But here the delta function will play a very crucial role, and it sort of gives you exceptionally important constraints. And it's basically the reason why the CFT in flat space-time, the flat holography CFT is not at all like a standard CFT. In particular, for instance, I can't just insert local operators at arbitrary local points. There is some non-local relationship coming from translation invariance. You know, because translation invariance is telling you that unless the 4 points is, let's say in a 4-point amplitude, are located in a very specific set of points where the sum of momentum is 0, you're going to not get something that's a scattering. You're going to get 0. So I can't just freely move an operator xi without affecting everything else. So there's some non-local relationship between the set of operators coming from translational invariance. And that is essentially been what people have been working on and trying to understand in the past.
So this particular structure is indeed more constrained than a CFT structure, but in particular is constrained by standard CFT constraints, right?
Yes, it's definitely standard CFT constraints are there, and then there's additional constraints.
So usually when I take the standard CFT constraints, I'm tempted to write 2-point function in the way I do, in a 3-point function the way I do, but that is not applicable because there is some other possibility that I don't consider probably. That's what you say.
Yes, exactly. So let me just give you this example. So for instance, the 2-point function argument, we usually use the argument, well, that the 2-point function between delta 1 and delta 2 is only non-vanishing as long as delta 1 is equal to delta 2. Right? That's what we conclude. But indeed, that's not actually true. Here's another possible conformally invariant structure is if delta 1 plus delta 2 is equal to d, the dimension of space-time, and then this is equal to delta of x1 minus x2. And this is also a conformally invariant structure. And indeed, this is the conformally invariant structure that shows up in scattering amplitudes. And it's this delta function thing. We don't see this in CFTs because we assume in CFTs we can move a local operator around in X space independent of everything else. And that we assume that the correlation function is an analytic function of X1s and X2s. But that's just not the case.
Also, unitarity, there's a standard type of unitarity there, which
does not apply.
Such an operator, right?
Yeah. Does not apply.
So okay, sorry, I'm a bit excited, but I was wondering if you will also say something about unitarity and things like that also. Like,
no, I wouldn't say, because at the moment no one knows.
I see. Okay.
No one. Actually, I'm in the middle of writing a paper about it. Maybe in a couple of months. Okay. Hopefully, I'll have something interesting to say.
Okay, so sorry for
No, that's okay.
But go ahead. Yes.
Okay. Well, I'm still at the review, and we're almost done with time. Let me just go forward. So in the same notation, in the same language, we can now also describe what a soft photon theorem is. So remember what a soft photon theorem is. Perhaps you guys already know what it is. I consider an endpoint amplitude, and I have an extra amplitude with an extra photon in it. And so that's this amplitude on the this diagram that I've drawn over here is represented by this insertion. There's an extra insertion of this SA, which is the soft photon operator, which I've defined over here. So as we know, in the low energy limit, there's a 1 over energy pole. So I multiply by omega to get rid of the pole and then take the omega goes to 0 limit. So by its definition, this operator SA extracts the residue of the soft pole. And the residue of that soft pole, I mean, I suppose if anyone here has taken, I mean, if you're taking QFT1, you will know is just this formula right here, which when you use the momentum parameterizations that I've told you in the previous slides, takes a very nice and simple form. Just log of pi dot q, and then you take a derivative. It's also clear from this formula that this operator S has a dimension 1 in this celestial holography story. And that's because log has dimension 0, and then the derivative has dimension 1. So that's how you can work out the dimensions in this simple case. See, that's what I meant. We don't even really need to do the Mellin transform. It's just very easy to work out the dimensions just by looking at formulas. Okay. So this is just what the soft theorem is. So again, this is just a review, so I'm going to go through everything. So what's been recently understood since over the past 8 to 9 years is that the soft theorems are in fact ward identities of these infinite dimensional symmetries that gauge theories have. In the case of the soft photon, and for every symmetry, there is a soft theorem, and vice versa. For every soft theorem, there is a symmetry. There's a one-to-one map. So the the symmetry that is associated to the soft photon theorem is what's called the large gauge symmetry. And when you have a symmetry, you can also hope to construct a current. You can hope to construct a conserved current. And this was done in a previous paper by myself and Dan as well, the same two authors, and it's related in this way. It's the shadow transform that's showing up. And we can at least do a sanity check. Remember, we said that this SA has dimension 1, and a shadow transform is a very unique set of transformations in a CFT. It's a non-local transformation that maps conformal primary operators to conformal primary operators. But it exchanges the dimension. Delta goes to D minus delta. So we know that this S has dimension 1, as we just discussed. So the operator J has dimension D minus 1, which is a sanity check. We know conserved currents should have dimensions D minus 1. But what is interesting is that the precise relationship is the shadow transform. This is not at all obvious at all. But it turns out to be the case. And we have proofs of this in even dimensions, but I think odd dimensional proofs, like why it's the shadow transform, is not really known. My understanding, at least as far as the even odd dimensional case, is that it works, but I'm not really sure why at this point. Okay, so this is just some explicit formulas for what the shadow transform, what the definition of the shadow transform. We won't really need it. The only thing for you to know is that it maps delta to D minus delta. And shadow squared is equal to the identity. Okay, and you can now work it out. I can work out the divergence of this operator J that I've just defined using the soft photon theorem, and you get this formula. And it doesn't quite look like the ward identity for a conserved current, but that's because, remember, these operators OIs are not local. So they have non-local charge distribution. And indeed, the non-local charge distribution is governed by the bulk to boundary propagator. And also, as we discussed, we expect this to localize in the massless limit. And it indeed does, because of this very nice formula. When I take the massless limit, it becomes a delta function, and you reproduce exactly the standard current ward identity for local operators. So indeed, in the massless operators are local. This is a reinforcement of that fact. And the massive operators are not local, but have this complicated charge distribution. Okay. Let's go on. So let's talk about soft exchange. Now we talk about soft infrared divergences. I
didn't quite understand when you say massive operators not local. I mean, that's because you are considering fixed momentum, right? But if you consider a fixed position, then they will be local, right?
We don't know that yet. We hope that's true, but that's not immediately obvious.
But if you use that basis and check whether a ward end satisfied, that don't you get delta functions?
No, you don't. Well, it's a complicated thing because you have to. That integral is very complicated to do, and we spent a lot of time on it. Precisely because of the non-analytic structure, you're supposed to extract the delta function singularities out of it, and it's just hard to do. But here's the reason why I don't expect it to be the case. Because here's a formula for you that the massive operators satisfy. I don't expect them to be local. Again, it's an open question, but I don't expect. So because the operators with dimension delta, if I take a shadow transform of the operator with dimension delta, you get the operator with dimension D minus delta. this is not the trivial statement, by the way. I'm taking this Mellin transformed operator over here, this operator over here, right? And I'm doing a shadow transform on both sides. And then it turns out that the shadow transform of this O delta defined in this way is equal to O of D minus delta, where I just substitute D minus delta in this formula. So this in fact suggests that the operators O delta are not themselves local, because there is a non-local relationship between operators with dimension delta and D minus delta. So you have to pick. It's probably the case that if I choose delta with imaginary part positive, so in the upper half plane, those are local, then the ones in the lower half plane become non-local. And so it's precisely, this is the issues why the set of all local transformations in a CCFT are yet to be completely understood, because actually it's coming from precisely this issue right here. But the fact that the massless particles are local, that is understood. That is well understood. The massless operators are local. Yeah, question? You see, just to be clear, locality is a stronger constraint than just saying that it transforms like a local operator. Just because something transforms like a local operator is not enough. Right? Like look at the shadow transform. The shadow transform relates a conformal primary to another conformal primary, but it's a non-local transformation. So one of these operators is, if it's local, then the other one cannot possibly be local. It's about the singularity structure in correlation functions, which is what defines local operators. But the singularity structure is really not understood because of translation issues in CCFTs. So it's not even clear how we would properly define local operators. Like in standard CFT, you would like to say, I think the nice result is that if I give you a correlation function of local operators in a Euclidean CFT, then the only singularities in that correlation function is when xi goes to xj. And if this is true, then you would say that all the operators in this correlation function are local. But now we have delta function singularities. We also have power law singularities. And it's just not clear what even we should call local at this point.
Just to be clear, I mean, when you are saying that the shadow operator O tilde D minus delta X is a non-local operator if O delta R is local.
Yeah.
What exactly do you mean? Because it's a function of X.
It's a function of X, but it's non-local because it's related. Suppose this is local. Right? Yeah. Then I have to do this integral transform. And even though it depends on X, it's still an integral over the entire space. So it has support on the entire space. Just because it depends on a single point doesn't make it local.
No, but for instance, the current, for instance, J, would you say that J times the Green's function?
Yes.
So the current times the Green's function, is it a local operator or not?
So a local operator in a CFT, again, there are many ways to define it, is perhaps you could also talk about it from the point of view of OPEs. You could say that if I take an operator OX1 and an operator OX2, then this 2-point function is singular as X1 goes to X2. So divergent as X1 goes to X2. So this is a property that local operators have to satisfy, which is, this goes beyond conformal transformations. It goes beyond the fact that these operators depend on just X1 and X2. You need this extra property of the singularity structure for it to be a local operator.
So Prahar, one probably related question / comment. I mean, if you have this kind of word identity for standard operators and you get delta functions on the right hand side, now if you instead of those operators insert shadows of those operators, then doing this transform you would expect not delta functions but some power laws, probably.
Exactly. That's
what
point.
You get. Is that what you get there also?
That's what you get. That's what I'm saying. That
I see.
Exactly. That's perhaps the best way to explain.
Yeah. Okay. Fine.
Okay.
Just to understand this O delta R, 2-point function of this operator will have delta function, or the O tilde will have.
In a standard CFT, neither will have delta functions. In a standard CFT,
in a standard CFT, no, but in a CCFT.
In a CCFT, O1 with O2 has a delta function. Which therefore means that O1 with O2 shadow has 1 over x12 to the power 2 delta.
So which behaves properly in the CFT sense?
I mean, again, as I said, it's not enough to just study 2-point functions. If you really want to make such strong statements, you have to somehow prove that this is a structure for all correlation functions. So just looking at 2-point functions is not enough to conclude anything about the local structure of the theory.
Okay, another point, if you have, say, some 5-1, 5-2, 5-1, 5-5 correlator, that in general doesn't have a delta function structure, but that doesn't mean that they're non-local, right, in general?
No. That's not what non-locality is about. I'm just saying that locality is about the singularity structure as x1 goes to x2. That's it, and it should
Yeah,
have.
so you said that non-local operators have in general a non-generic. I mean, they don't have the delta function dependent structure. You have
not all the time. They could still have. So, for instance, it's still true that if I take, if it's true that O1. You see, this is a complicated definition. If I take the 2-point function of O1 with O2 standard CFT, and I just look at x1 to the power, this is x1 to the power 2 delta, and I look at the correlation function of the shadow operators, this also has the form 1 over x12 to the power 2 d minus delta in this case, right? So you can clearly look at the 2-point function of the shadow operators, and you see it has exactly the right local and singularity structure.
Yeah.
Does that mean O1 tilde and O2 tilde are local? No, we can't conclude it from just looking at the 2-point function. The crucial thing is you have to look at n-point functions for arbitrary n to make any strong conclusion from it. This is the problem. You can't just look at 2-point functions or 3-point. It might just be that just the 2-point function still continues to have the form of a local 2-point function, but that doesn't mean that the operators themselves are local. This is why when you study CFTs, it's a much stronger assumptions go into the definition of a CFT than simple conformal symmetry. You don't just say conformal symmetry. You say there's a conformal symmetry, there's a basis of local operators, which is an assumption. You assume that they have some set of OPEs, which again follows from, and so there's a whole list of assumptions that goes into, into our definition of a CFT, which is the reason we are not calling this flat space guy a CFT, and it's been given a different name, a celestial CFT, just to make sure that there is a distinction and we don't fully understand the
and moreover, in the EDS-CFT direct dictionary, when you have a field defined by the bulk to boundary propagator, which is multiplied by some boundary operator, do you say that the bulk operator or the bulk field is a non-local operator? You don't, right?
I mean, from the CFT perspective, it is the non-local. It is definitely non-local.
But from the bulk perspective, it is not, right?
No, it's not. But those are two different perspectives. Locality with respect to bulk is not the same thing as locality with respect to the boundary. That's not to say they're not related, but you can't. Yeah, they're two different viewpoints. Okay, I'm almost out of time, and I'm still at the review. Okay, let's go through this. Let's look at infrared divergences, or just soft exchange, because I'm assuming d greater than or equal to 4. Again, by soft exchange, I mean diagrams of the form in which you have a soft particle which goes through the, and there could of course be multiple such soft particles, or it could be infinitely many loops, whatever you want. And the structure, this is a well-known fact from just Weinberg, in the textbook Weinberg, you will find it, that the amplitude factorizes into this form with the e to the minus gamma. And this is the form of gamma. This integral is something that you would have to compute. And again, it's computed at least in 4 dimensions in Weinberg. But I'm going to give you a different representation of this integral, which will be useful for our purposes, which is the following. So you can then check, if you evaluate all of this, you use the parameterization of the momenta that I told you about, you perform this integral over L, and this is what you end up getting over here. So you get a real part, A1, which is the only part I'm going to talk about for the bulk of this talk. And I'm going to make some comments about the imaginary part later, again, which it doesn't look like I'll have time for that. So A1, which just takes this very simple form. So this J is the same J that's appearing in the soft theorem over here. This J is this, where is it? It's this J over here. It's the same operator, well, same function. So you can actually check that by explicitly performing this integral, that a1 is just equal to the integral over of the square of that operator. And this alpha is essentially where all the infrared divergences come from. So you can see that when d is equal to 2, remember capital D is d plus 2. So d is equal to 2 is 4 dimensions. Then this alpha is roughly log of lambda over mu. So that's logarithmically divergent. This is where the infrared divergences come from. But in d greater than 2, this alpha is roughly mu to the d minus 3, mu to the d minus 2. So in the mu goes to 0 limit, alpha goes to 0. So there are no IR divergences in higher dimensions. Okay, but we won't care. The point is just we let it be alpha, and then we'll deal with alpha is either infinity or 0, depending on what limit I'm interested in. Okay, so so after all of this simplification, we go back to the original formula that we wanted to prove, but now hopefully everything except one thing has been explicitly described for you. We wanted to prove this relationship here. That's what we started with. These soft operators, S has been defined for you. It's the soft limit of, these guys are limit omega goes to 0 of omega OA. Remember what this A was. This A is the polarization of the photon. There are depolarizations. That's what this A stands for. So that's why this S has an extra subscript of A, it tells you the polarization. These are the soft factors in the case of the soft photon explicitly given here. And then this is the gamma, the infrared divergent factor. And there's also the imaginary part, which I'm not going to talk about for now.
Sorry, Prahar, could you go back to the previous slide, please?
Yeah.
You have this integral expression here, and then you have this expression for gamma in terms of this J operator.
Yes.
And it's clear these two are the same. I couldn't see it.
Oh, no, it's not clear. It's a calculation. It's not clear, but it follows math. It's a math. It's just mathematics. You just have to go through the calculation. That's it.
Okay.
But it's not obvious.
Okay. One more question. This in the integral expression here, are you using sort of the same approximations you use for the Eikenall approximation, in the sense that in the hard propagators you ignore the k-squared term?
Yes.
Okay.
Yes.
Okay. Thank you.
Indeed, that would have given us higher order contributions. We could have done that. We could have kept that in. And in fact, one of the things that Ashok has done in his papers is to actually keep track of these higher order contributions to derive these higher order soft theorems. So it's possible to do. It's just more cumbersome.
Okay. Thank you.
Yeah. In any case, the point is that whatever those extra terms are, they will not contribute to the leading order divergence anyway. So we are just interested in trying to reproduce leading order divergence. Okay. So anyway, this red boxed equation is now what we would like to prove.
Sorry, I'm sorry. One more thing. I mean, here you're considering basically these ladders, just diagrammatically on the previous slide, you have these crossed ladders basically, right?
Yeah.
And you can show that these are the only things that contribute significantly. Yes. There are no other graphs.
There are no other graphs at leading order.
Okay.
Yes.
Thank you.
And this is a very good question. It's been, it's been addressed in Ashok's paper. There are other graphs. If I want to go to subleading order, then I need to look at graphs which go like this and then go all the way inside the graph somewhere. So, just goes inside, and those correspond contribute to subleading orders in the soft expansion.
And by leading and subleading order, you mean leading and subleading order in lambda or mu?
The leading order divergent contributions to alpha in when you take the limit mu goes to 0.
Okay. Okay, thank you.
Okay.
What about loops in the photons?
Yeah, they all factorize because photons are nice in abelian. So you can basically show that a diagram that's of this form, a diagram that's of this form with say 2 loops, this is just equal to this diagram whole squared.
Okay.
With the factor of 1/2 factor, some symmetry factors and whatnot. So you just have to compute this one loop diagram. That's where this one loop integral is coming from. And then everything else exponentiate. That's why it's an e to the minus gamma. So it's an exponential factor. And then you just have to compute a single one loop diagram. This is all in Weinberg, just standard stuff. Chapter 13 of Weinberg.
No, I was wondering, say, an electron loop in the photon line, but I guess if the photon is too soft, that won't contribute.
They won't contribute. Yeah.
Okay.
Those are all subleading in the soft expansion. But also, actually, no, I understand what you mean. Also, there's another thing. The electron loop, suppose something like this you want. So what would I have to do here? So I would have to take, let me think about this. I mean, I think that the diagram that you're looking at, something like this, is that what you're thinking of?
I can't see anything.
Oh, sorry. I remember I'm assuming that all the UV renormalization has already been done. So if I have a diagram that looks like say this sort of diagram,
Or maybe the vacuum polarization diagram. I mean, in the
those will all
line.
contribute to renormalization of the coupling constant,
Yeah,
right?
yeah.
We've done all of that. So this will correspond to renormalization of this vertex factor. All of that is done. So this E squared that's appearing over here is the renormalized coupling constant. So I'm assuming that you've completely UV renormalized the theory, and you might have to introduce a UV cutoff for that. Let's assume we have done that. We've renormalized. Now everything I'm working with are the renormalized coupling constants, the renormalized fields and propagators and whatnot. And then this E squared that's appearing here is the renormalized gauge coupling constant. And now I'm trying to understand the low energy structure of this renormalized theory.
Okay.
Okay. Okay, so that was done. So hopefully the structure is clear to you. Now what I'm going to show is that all of these complicated formulas, which here you see was derived by Weinberg using Feynman diagrams. So he had to sum over all of these Feynman diagrams. And indeed, trying to do these sum over Feynman diagrams is even more of a headache for non-abelian gauge theories. So that's much more complicated. I'm going to basically show you that all of these results are just a consequence of asymptotic symmetries. Okay, so let's just go through this, I think, since I'm really out of time. Let's just quickly. So remember, the goal was to find two things. I have to define, there are still two things in this formula which I haven't defined for you. The first thing is this UI, which I have yet to define. And the other thing was S soft, which is a function of all the soft operators in my theory. And if I can define these two things for you, then you can compute the left-hand side, because I've defined now, everything has been defined. And then the goal is to, if I can find UI and S soft for you, you should be able to compute the left-hand side and then check that you get the right-hand side. So I'm going to show that that's actually possible using just symmetries. Okay, so the first step is to identify in gauge theories, what are the soft operators? So we've just discussed this. The soft operators, the first of them, one of them is just S. And the other soft operator is the edge mode. So what is soft? Soft means low energy, which means in space-time, it's the infrared mode. It's the mode sitting out at infinity. And indeed, that's the mode that we are going to refer to as C. So C is the value of the gauge field at the boundary. Okay, so these are the two soft operators in gauge series. So I have to write down an action that's a function of S and C. That's the goal. So I'm good.
And this is the boundary of this cry.
Boundary of scry, you just take it as spatial infinity. Yeah. There is an identification between the boundary of scry and the boundary of spatial infinity with some antipodal map that's going into, the details are unimportant. It's just the point that it's a boundary of a Cauchy slice. That's really the only thing that'll be important.
Okay.
Okay. So I want to compute this. Now I'm going to first simplify my job and do everything step by step. So let's first.
Sorry, could it also be just, if it's the boundary of the Cauchy slice, could it also be just the cut of this cry?
What cut are you looking at?
I'm saying, you're saying it's a boundary of a Cauchy slice. So could it also be just any?
It could roughly be.
Okay, okay. I got it. Yeah.
I mean, so let me draw the diagram for you. The Penrose diagram is something like this.
I got it. Yeah. So you want this special.
Scry plus is this surface here.
Okay.
And so the boundary of scry is this, is sort of this sphere that's sitting over here. So this SD.
All right, thank you. Thanks.
Okay, so let's simplify my work first. I'm going to start by assuming that there are no external soft operators. So there are no S's, that there are no S insertions. And I'm just looking at the correlation functions of the UIs. So if there are no S insertions, then I can integrate out S completely. And I'm going to get an effective action for just C. I'm going to start by trying to construct this effective action. And then I'm going to integrate in S after that. Just so I can go step by step. So I'm going to construct S soft using symmetry. So let's do that. So how do we do this? The point to remember is that these theories have these large gauge symmetries. And what is a large gauge symmetry? It's just the standard gauge transformations that you're all familiar with, except that they do not vanish at infinity. This is crucial. So gauge symmetries that don't vanish at infinity are physical. They're physical, they have physical consequences for the S matrix. And there's an order parameter for these symmetries. It's the Wilson line. And as you can check, the Wilson line transforms exactly as you expect under gauge transformations, except that this is, because this is C over here, this is a Wilson line on the celestial sphere. So it's a Wilson line. Let me draw it out here. This was again what I drew. So this is the sphere, and it's a Wilson line that starts at some point X naught here and then goes to some point X, whatever I said, X over there. So it's a Wilson line that's sitting entirely on infinity. So this Wilson line is invariant under small gauge transformations, which are unphysical. So it's good that it's invariant under that, but it transforms non-trivially under large gauge transformations when epsilon is non-vanishing at the boundary. Okay. Now in standard quantum theory, the Wilson line picks up an expectation value. In particular, the usual expectation value that is assumed in perturbation theory is that the gauge field vanishes on the boundary. We assume this. So the expectation value of C is 0, which means that the Wilson line has an expectation value of 1. So these large gauge symmetries are spontaneously broken. And indeed, they're spontaneously broken down to the global symmetries. And so global symmetries are something we have known for a long time. So there's no need to talk about this, but the point is that there is actually this larger class of symmetries which are spontaneously broken in the vacuum of quantum field theory.
Wait,
all right.
Why is it global? Because even though the epsilon is still your, it does not vanish at infinity, but it's still direction dependent. So X and X naught is the same. I mean, the value is not the same. So it's
the direction dependent gauge transformations are spontaneously broken. The only set of gauge transformations that are not spontaneously broken are the ones which are constant. As you can see from this, because I need a set of gauge transformations that are not spontaneously broken are the set for which this is 0 for all X. And that's only the constant modes. So the usual global U1 transformations that you're familiar with are not spontaneously broken. They're actual symmetries that are exact symmetries in the vacuum that I'm sitting in. But the point of what we have learned in these past few years is that in the QFT vacuum, there's actually a larger class of symmetries which are spontaneously broken. And we know that spontaneously broken symmetries are powerful. I mean, even if they're broken, you can actually make a lot of non-trivial conclusions from their existence. So that's what I'm going to do here. So in particular, remember C was a gauge field. So it just transforms like a gauge field under these transformations. So I'm now going to try and write down an action for this. So let's do that. So what's the action that I want to write down? Again, I'm following the standard lore of spontaneous symmetry breaking. How do you write down an effective action for the pions at low energies? And I'm just doing that, but I'm doing it for the large gauge symmetry. So the first thing to do is that you want to write down an action that's invariant under all the symmetries, even the ones that are spontaneously broken, except that the spontaneously broken ones happen to be non-linearly realized in your theory, which is exactly happening here because the large gauge symmetries are acting non-linearly on your C over here, as you can see. There's a non-linear action. Okay. So in other words, the action has to be what I mean by all of this is that the action has to be gauge invariant. Not at all surprising. So in other words, it has to be a function of F, only of F. But here's the problem. When I have no magnetic charges, and I'm going to assume that this is the case, then the field strength vanishes on the boundary. Because remember, the integral of the field strength, integral of F, is the magnetic charge. So if I have no magnetic charges, then F is equal to 0. So this would suggest that the action is completely trivial. There's absolutely nothing that you can write down. That's not good. But here's what saves us, and this is one of the reasons. When you have a cutoff, either mu or lambda, it doesn't have to be the IR cutoff. If you introduce an explicit factor of the scale, then these large gauge symmetries are also explicitly broken, in addition to being spontaneously broken. And so we also know how to deal with explicit breaking. We do this with the SU2 isospin, which is explicitly broken. You sort of give a tiny mass term to your action, which characterizes the amount of explicit symmetry breaking. So we know how to deal with that as well. So all I'm going to do is I'm going to include in my soft action a small mass term for the gauge field C. And this term now explicitly breaks the large gauge symmetry, but it preserves the global U1 symmetries. The global U1 symmetries are still exact symmetries of the theory. Good, almost good, but now we have made one more assumption that I'm going to have to relax, and then we are good. And the assumption is that of locality. So we are coming back to locality again. In writing down this action, I have assumed locality, but I've assumed boundary locality, because this is an effective action on the boundary. And there was no need for me to do that. There was no reason for me to do that. What I need to reproduce is bulk locality. This is a crucial fact. Whether the boundary itself is local or not is something we don't yet know. And in fact, we'll see is not the case. So we'll generalize this a slightly bit more and write down a generic quadratic non-local action.
Sorry, why is a global symmetry still present even if the gauge symmetry is explicitly broken?
C doesn't transform under the global symmetry. C under the large gauge symmetry, C goes to C plus D epsilon, and epsilon is a constant for the global transformation. So for global transformation, C just goes to C. So this action is, it's sort of trivially invariant under the global transformations.
Sorry, Prahar, just to make sure I get the dimensions right, you're in a bulk D plus 2 dimensional space.
Yes.
And
yes.
This action is happening all at the celestial sphere, D-dimensional celestial sphere.
Yes, exactly.
Okay, thank you.
We're trying to find an action, sort of at least part of the action of the celestial CFT. And so this is the point. The point is that we want to write down this boundary action, and the boundary action should reproduce bulk physics. So we know bulk physics has to be local, but that in no way implies, at least trivially, there's no way implies that the boundary physics has to be local. Now, this is true in ADS-CFT, but that's a very special property of ADS-CFT. This is one of the reasons ADS-CFT works so well. We know it's not true in flat spacetime. We also know it's not true in DS. So the fact that it works in ADS-CFT is actually a special case. We shouldn't expect that to happen all the time. So we should at least start off with a general assumption that it is non-local. And then if it tells us, if we find at the end of the day that it's local, then that's great. But if not, as we will see, we will find that it's not, then that would actually tell us that the boundary theory is not local with respect to boundary dynamics, even though it reproduces bulk local physics. And another reason to not expect it is because, after all, this is the soft mode. This is the soft sector of the theory. The soft sector of the theory is infrared. So these are long wavelength effects. So why should long wavelength effects be localized in any sense? We don't expect them to be localized at all. But there will still be a surprise that will come to. Okay, so I've now told you what the action is. You're almost done. I just now need to tell you what the operators UI are, and then you have everything. You can now compute everything you need. And we can also work out what UI is, also based on symmetries. And the way I'm going to do that is to just look at how everything transforms, and then I can extract the structure of UI. So this is the large gauge transformation of this operator OI, and this comes from covariant phase space analysis. Phase space. So we know how these operators have to transform. This also comes from semi-classical analysis of the soft theorems. Something that follows from the soft theorems, you can actually show how they transform. So the operators transform in this sort of non-local way. And again, remember everything localizes for massless states. So massless states, I think, really have this locality property down. All right. So it's almost trivial. It's really trivial to work out the action, the operator UI. Because remember, C transforms like C plus D epsilon. Remember, C was flat. which means that I can write C is equal to d theta, which tells us that under large gauge transformations, theta goes to theta plus epsilon. And it's almost trivial to write out the operator ui, because all I need is that when I shift theta to theta plus epsilon, I should reproduce exactly this factor, which I do. So here, if I take theta goes to theta plus epsilon, I'm going to reproduce exactly that factor. So it's kind of just based on symmetries. It's very easy to simply work out what this operator ui has to be. This is the only structure that this is the only possible structure that it can take. Remember, other possibilities are it depends on f, which is gauge invariant. So I can also include terms in here which depend on f. Since that doesn't transform, it's not going to play any role, but f is also equal to 0 in the theory that I'm working in the absence of magnetic charges. So indeed, terms which depend on f play a crucial role if the particles that I'm considering are also magnetically charged, if they're dions. And in our paper, we have a discussion on the generalization of these things to dions as well. I'm not going to talk about it here.
Sorry, so theta was the gauge parameter as a function of x?
No, theta is just the gauge field on the boundary. So here I've shown you, so let me write down everything. C is the gauge field on the boundary of Scri. It's the soft mode. But we know in the absence of magnetic charges that dc is equal to 0, f is equal to 0 on the boundary. That's because the magnetic charge is by definition integral of f. And so if there are no magnetic charges, then f is 0, so dc is equal to 0, which means that I can solve c is equal to d theta.
Right. So the gauge field is pure gauge at the boundary, and theta is the gauge parameter for that.
Theta is that, yeah. And so under gauge transformations, theta goes to theta plus x.
Thank you.
Okay, so I think we have all the ingredients now, and now it's just a matter of computing things. So the final thing
could you go back
to
the previous slide?
Yeah.
So UI is like so OI transforms under a gauge transformation in this fashion.
Yes.
By this equation. So from there, how does it follow that UI has to have this form?
Well, it has to have this form up to another factor. It could also depend on UI hat as a function of f. Because just look at how this UI transforms. How does this UI transform? So under large gauge transformations, theta goes to theta plus epsilon.
True.
Right? So when theta goes to theta plus epsilon, the epsilon part precisely comes out over here and picks up this entire extra factor that's sitting out there. So this tells us that UI under gauge transformations is precisely this factor right here times UI under large gauge transformations. The only part of this operator that we cannot fix is this dependence on f, because after all, it's gauge invariant. So we could write down anything which depends on f, but f is 0. So there's actually absolutely nothing you can write down that depends on f.
Yeah, but the OI itself could transform. The OI in this.
No, that's the point. The OI depends only on the hard modes, and these symmetries don't act on the hard modes. It acts only on the soft sector of the phase space. So it acts on all the soft fields, but not on the hard fields.
Okay. Okay, go ahead.
Prahar. Sorry, you'd written down an action which was C wedge C star at some point for C. In that action, should I also substitute C is equal to d theta?
You should. Yes, I have it right here.
Thank you.
But this is not the action. This is the local action, and this was written down assuming boundary locality.
Okay.
Which is not an assumption one should make.
Yes.
So the correct action is this.
Right.
This is the non-local generalization of that action.
Right. And here again, the actual dynamical variable is theta.
Exactly. Again, this will not be the case when you have magnetic charges. Then the actual dynamical variable will be C.
Okay. Thank you.
But you can only have magnetic charges in 2 dimensions, because particles can only be dions only in 2 dimensions. So anyway. That's a special case of 2 dimensions, which we do deal with in our paper. Okay, so I think you have everything now. The only thing that you still don't have is this P inverse, which is just some propagator of the C fields. And it's something we have to work out based on matching everything. And we'll just work it out right now. All right. So let's finally get to the result. So I've defined UIs to you guys. Now you take a product of all of these UIs, all particles. You just end up getting a term that looks like sum over QI, KD. And this sum over QI takes a very simple form. It turns out that this entire sum over QI can be written as del A JA of X, where this small JA is just the shadow transform of this curly J, which was showing up in the soft exchange. Remember, A1 was integral of J tilde, J squared, curly J squared. It also showed up in the soft theorem. SA O1 to ON is precisely JA, right? So it's showing up all over the place. So this quantity in the bracket is precisely this del AJA. And then I can do one more step where I integrate by parts. This derivative I integrate by parts. I have to keep track of the zero mode of theta, which simply gives me sum over charges. As we'll see, this integral over the zero mode will give me charge conservation. Okay, let's put everything into the full action. Here's what I have to do. So the full soft path integral. Now, at the moment, in the absence of external soft insertions, I have these UI insertions. I have a path integral over d theta. This is the kinetic term, which is coming from S soft. These are the terms that I discussed in the previous slide. These guys are coming from the product U1 to UN. And this is just the Gaussian path integral. It's very trivial to do. You can do it, and this is what you get. The integral over the zero modes. Remember, everything over here is simply derivative with respect to theta. So the zero modes do not have a quadratic action. They just have a linear action, and so they'll give you a delta function. Or in this case, a Kronecker delta function, because the gauge group is compact. So theta naught lives from 0 to 2 pi. So it's a compact integral. So you just get a Kronecker delta function for charge conservation. And then you get this factor, which is just the J P inverse P, or J P inverse J. Now, in order to match out everything, in order to match the result to our soft exchange, we need this. Remember, this entire factor has to match to e to the minus gamma. And this is gamma over here.
Sorry, could you please remind again why C wedge C star got you this E insertion?
C wedge C did not get me this. Here, this is the action I'm working with.
Yeah, so
C wedge C is the action. Yeah, so this is where did this action come from? It's just a non-local generalization of this action. So this first action came from the usual way we deal with explicit symmetry breaking. You just add a mass term. So you give the gauge field a mass term, a slight mass term, which depends on your IR cutoff. And the existence of this mass term will explicitly break gauge symmetries, as we well know. So that's how we wrote this first term. But we made a hidden assumption when we wrote down this first term, an assumption we sort of, without really thinking, we make in quantum field theory. It's about locality, which is fine when you're doing quantum field theory. But now what I'm trying to do is I'm trying to write down a bulk action, which reproduces, I'm trying to write down a boundary action, which reproduces bulk dynamics. And bulk dynamics has to be local. Boundary dynamics does not have to be local. So this implicit assumption of locality that we have made is incorrect. We shouldn't be making that assumption.
True, but the boundary action should follow from the bulk action in some way, right? I mean, you can't.
It should follow. But I'm trying to argue that we don't need to know how, and in order to figure that out, you would have to evaluate the path integral. But the goal of my talk is to show that we don't need to care about how it's done. We can fix it by symmetries.
Okay.
I mean, if you want to perform the path integral and work out what the bulk term is, you could do that, and you will get exactly this. Because the idea is that everything is constrained by symmetries anyway, so there's nothing else it could be.
Okay, go ahead.
Okay, so this is the non-local generalization of that action, and then this is the action I'm using to compute the 2-point functions. As I've said here, This is where that action is coming from. This is S soft, that non-local action up there.
Sorry, Prahar, I forgot the difference, but I forgot what little j and curly j were.
Yes, it's right here. So it just turns out that this sum over q, I've written it right here actually. This sum over q. So this kd, remember, was, where is that showing up? That's showing up in our definition of ui. Let me erase all of this nonsense. So this shows up in our definition of ui right here, this kd. Now, when I'm computing the expectation value of ui and all the way up to un, I need to take a product of all of these. So I'm going to get a sum over ki, qi, kd, which is just coming from a sum of these terms and then this qi term. Those are the only two things that depend on I. And then you can show that, just as a mathematical fact, that this sum over qi is divergence of a certain current j, which is the shadow transform of this curly j that I've defined previously. This curly j was showing up in A1. It was showing up in my soft theorem SA.
Yeah, I remember curly j.
Okay,
but this is the first time we've seen little j. Is this right?
Can you? Sorry,
have we seen little j before in this talk, or is this the
no?
First
this is the first time I'm introducing it here.
Little j. Thank you.
It's just the shadow transform of j. Okay, so we're basically done. This little j over here is just a shadow transform. And so in order for everything to match, everything to make sense, this is what we need. We need this factor in the exponent that's showing up here to be precisely, well, without the minus sign actually, without this minus sign, we need this to be equal to gamma.
Sorry, and this little PAB was dependent on mu and lambda, right?
PAB is dependent on mu and lambda.
Okay, thank you.
And we'll figure out the mu lambda dependence right now. So that's what this is. This is the thing that's gamma. And that's what this equality stands for. And we have to find PAB such that this equality is true. And it's easy to fix it. It's just a matter of some computations. Here's what PAB is. And alpha over here, remember, alpha is the thing that depends on mu and lambda. So all the mu lambda dependence, this is just integral mu to lambda, d omega, omega to the d minus 3.
Sorry. Could you go back to the previous slide?
Yeah.
The right, oh, I see. The right-hand side here also depended on mu and lambda.
Yeah, through alpha.
Through alpha. And in the Feynman diagram point of view, that came as just a limit of the integral.
Just the limits of the integral.
Okay,
if I can show you that, let me remind you here. It just shows up from these limits.
Those limits. Thank you.
Okay. Where are we? Here. Okay. So I just need to match up both sides.
So thing is, why should gamma be jx whole square integral?
That's because that's because of this calculation right here. That's because of this calculation right here. So gamma is defined as this integral, which is something that you can check in Weinberg. And then if you explicitly work it out using all the momentum parameterization that I introduced in the beginning, you can then show that it reduces to this very simple form, where it has A1 plus 2 pi A2, and this A1 has precisely the structure of J square. And A2 is an imaginary piece which has a much more complicated structure, which is part of our next paper. We haven't discussed it in this paper. I'll probably flash a slide at the end, but I don't think I'll have time for that. But so what I'm showing you right now is how to reproduce A1 itself, but not entirely A2. To fully solve the problem, you would have to reproduce A2. And I think I have the answer for that, but it's much more complicated.
So it's A2 that's it. So I think that keeps track of the fact that particles don't really become straight lines at infinity, at least in 4 dimensions. But there's a lot of correction to that.
Yeah. And it's also the thing that gives us the crossing symmetry problems, because it depends on in and out particles separately. You see here in A1, there was no distinction between in and out particles. I can move into out and it won't actually affect the structure of A1 at all. But it's precisely this phase part of gamma that has this crossing symmetry issue.
Thank you.
Okay, so is that clear? That's why gamma, so that's why this gamma was equal to this J squared. Integral of J squared.
So there must be certain circumstances in which A2 can be neglected. Otherwise, this.
No, there are no circumstances in which it can be neglected actually.
But then, how does it make sense?
There is another part of the soft action. And this is not the only part of the soft. As I mentioned in my comments, final comments is that there are other soft theorems, there are other soft factors, there are many other things. This is just a part of the action. Then you can actually, in order the full celestial CFT action has a whole bunch of soft terms, a whole bunch of extra terms you must add to the action to reproduce the full scattering amplitude. I'm only reproducing this one part in this talk, and I've already reproduced, at least it's not in a paper yet, but I have reproduced this phase part as well, and I'll flash the formulas in my very last slide for you to look at.
A2 goes away in taking mod squares of amplitudes?
In mod squares, it goes away. So if I'm interested in crossing, if I'm interested in differential cross sections, then I don't care about this phase.
So often people don't worry about A2 for that.
Yeah, this is actually the problem. You will not see people discussing A2 in any QFT textbook because they just throw it away, because we only care about differential cross sections or decay rates and that sort of stuff. But as you know, if I'm interested in unitarity of the S matrix or crossing symmetry properties, then this S matrix part is actually. Okay. Where am I? Here. Okay. So I just need to find a P such that the left-hand side is equal to the right-hand side. And it's clear that there is a J relationship. So this JA is precisely showing up. This J, there's this relationship over here. So there's a curly J hidden inside over there. There's a curly J hidden, two factors of curly J hidden on the left-hand side. There's also exactly two factors of curly J hidden on the right-hand side. So we can remove them. And remember, this has to be true for any choices of curly J, because it has to be true for any choices of in and out states. It's independent of the scattering amplitude, which I'm computing. So when you rewrite everything in terms of curly J, then you factor out the curly J pieces, you can extract out the structure of PAB. And here's what it looks like. It's some monster. Okay. But there is something very nice hidden inside of this. I don't think I told you what this I is. IAB is the conformally covariant tensor is delta AB minus 2 XA XB over X squared. So it's just that. So this is the tensor structure that you get for P inverse. So I can plug it into the action, now this is my claim. This is the full action. This looks horrendous. And it's the first thing to realize is that it is non-local, as we expected. But as we assumed it was non-local, and if it turned out to be local, then that's great. We've learned something new about physics, but it turns out it's not local, just as sort of was naively expected, at least.
And you're going to say C is equal to d theta in this.
Yes. Everywhere C. The reason writing it is that it's easier to generalize when you have magnetic charges. Then you no longer want to write it. But here's the cool thing. Here's another way of writing that same action. If I write it in terms of the shadow transform of C, it's local. This I have absolutely no intuition for. I have no idea why, but it seems this is just true as a mathematical fact. So this immediately suggests a very interesting, in my opinion, conjecture that the boundary theory is a local theory of the shadow transformed operators.
Okay, I think that's cool.
But not in terms of the original operators that show up in the bulk. But again, I have no intuition for this. I don't think anyone expected this. It's a very, in my opinion, a very fascinating result.
But the operators were sort of simple, written in terms of C rather than the shadow transform, right?
Yeah, the bulk operators were simple, written in terms of C.
Okay, thank you.
But they are not; those are not the set of local operators on the boundary. So as I said, as I've probably mentioned now multiple times, there is bulk locality, there's boundary locality. The original operators, the ones that were simple, the C operators are obviously local operators with respect to the bulk, but the local operators with respect to the boundary are the shadow operators.
Right, but the insertions, these U insertions.
No, here I have the U insertions right here for you. They also end up taking a simple form written in terms of the shadow mode.
Thank you.
So it also simplifies for the in terms of the shadow.
But one thing is that this action has no dynamics. This is soft.
No, it does have dynamics because C tilde is d theta. Yeah, I keep not writing that.
Okay.
Well, C tilde is shadow of d theta.
Right.
It does have dynamics. And okay.
In the last time in the integral, it's just C tilde and not C tilde times J tilde. So it's like
no, this is not the action. These are the set of operators. The action. So when I compute u1 un, this expectation value, it's going to be integral over d theta e to the minus s soft, and then u1 to un. So this u1 to un factor is what I've shown in this box, and this soft factor is what I've shown in this box.
Oh, I see.
No.
Okay, yeah.
No, wait a minute. I mean, shadow of d theta is not going to be a simple derivative of some function, right?
No, it's not. It's not simple. That's my point. It's not simple and definitely not even local when you write it in terms of. It's still going to be derivative of something. It's not going to be nice and simple or local when you try to write everything in terms of bulk quantities. But that's not what we should try to do. What we should try to do is that there is this whole set of boundary quantities that we want to write. And then there is a map, there is a dictionary that tells you how to go from bulk to boundary. And that dictionary involves doing this extra shadow transform and then also doing this bulk to boundary propagator business in order to match from the boundary to the bulk.
The fact that
can you write shadow of d theta in terms of d of some shadow of theta?
You can actually. You can. Those are the things called the mirror modes. You can actually define it in terms of d phi. It's possible. Yeah.
Sorry, the fact that your original gamma was basically local in terms of looked like a simple expression, right? J tilde j squared integrated.
In terms of curly j, it looked nice and simple.
Yeah. Right. So the fact that this locality here is reproducing that simplicity.
Exactly.
So in a way, given that formula was nice, simple, and looked local, it's not surprising that there's something.
No, it's not surprising at all. But again, perhaps you could, I mean, that's just pushing it back to saying, why should that formula have looked simple in terms of curly j? Again, that's for me just a mathematical fact as of now. I don't really have intuition for where that came from.
Okay, thank you.
Okay.
So this there's some scale symmetry in this action. Should I see some sort of scale symmetry in this action? Or conformal symmetry in this action?
Yeah, this action is, well, we have to be a bit careful in that, yeah, we have to be slightly careful because remember, by introducing an explicit cutoff in omega, right, we have broken conformal symmetry slightly. Because, you know, for example, one way, there's a conformal symmetry which takes xa to lambda xa and omega to 1 over lambda omega. So this is the scale symmetry of conformal transformation. But because I introduced a cutoff mu, this scale symmetry is no longer an explicit symmetry of the theory. Now I can think of it as a symmetry as long as I also rescale my mu appropriately. And then it's a symmetry.
So where is mu hiding in this box? I mean, this
in
is
alpha. In alpha. So the alpha is sort of this coupling constant in the theory. So you have to, as long as you effectively rescale the coupling constant, then you also have scales. You have the full conformal symmetry. But this is a tiny thing you have to be a bit careful about. I mean, strictly speaking, you could just say this. I've introduced a cutoff, and this is also true in standard QFT, of course. When you introduce a UV cutoff, you don't really have complete Lorentz symmetry. But after you, in the limit where you take the cutoff to infinity, you have conformal. You reinstate Lorentz symmetry. That's what's happening here as well.
Yeah.
Could I think of this mu, Prahar, as putting the space on a sort of disk, like cutting off instead of being on scri plus and scri minus, just being a disk times time.
Yes. Well, yeah, exactly. This mu actually you can think of as wait, let me draw it here actually. So this is the Penrose diagram of Minkowski space, and you can think of mu as this cutoff in this space, so r less than 1 over mu, and this space inside, this is actually ADS. So you can think of ADS as this, including this cutoff, you can think of Minkowski space as this ADS, and taking the limit mu goes to 0 is the large radius limit of ADS.
I see. So if we were in a bulk 2+1 dimensional space, would that, I mean, it would be like a disk, and then there's time.
Yeah.
And then I'd have to be careful about the boundary degrees on the surface of the disk, right?
Yeah. Yeah.
And that's all these modes are basically those, right?
Exactly. Yeah. Yeah.
Sorry, with this, is there a relation between standard ADS CFT also?
There are some works on this. The issue with doing the large radius limit of ADS is that you have to take the limit exceptionally carefully. And at some point, the problem is that the boundary of ADS is completely smooth. I mean, in its time, there's no sort of discontinuity on the boundary. But in the limit, we know that in Minkowski space, there is an antipodal discontinuity, in the sense that fields that are coming in from this point in this limit should end up along this line. It has to be antipodally matched. But you see, if I try to do the same limit on ADS over here, it's completely like if I was to try and take limits of the ADS region, then a limit coming in from here would end up matching precisely. In other words, the ADS matching condition is the same angle matching condition. And this,
in ADS, if I send something inside from the boundary, boundary Lorentzian cylinder, it will end up on the other side, right?
Yeah, it will end up on the other side, but it.
So in that sense, it's the same kind of antipodality, right?
Yeah, yeah. But the problem is that the antipodality is very clear to see from when you go through the bulk, but we should also see it when you go direct just through the boundary. And that's the point that is sort of missing. So in other words, think about this, think about flat spacetime as the Einstein cylinder. You wrap it around on the Einstein cylinder. So what does that look like? So if I wrap it around on the Einstein cylinder, this looks like, my drawing is going to be terrible here. Something like this, and that's spatial infinity. Yes. And on the Einstein cylinder, it's clear that there's an antipodal map, because a light ray that's coming in this direction, it naturally goes across and goes antipodal in that direction. Mm-hmm. And so the antipodal matching in flat space-time is sort of very natural. But when I'm sitting on ADS, if I now think of this as ADS, and so this is the boundary of ADS here, and I'm moving along just through the boundary, I'm moving along in this direction, there is no discontinuity at any point. If I start out in a trajectory that's on the North Pole, it's going to remain on the North Pole forever. It's never going to suddenly jump to the South Pole. But we need such a jump to exist in order for the limit to be sensible. And this is, I think, the big issue that people have not been fully able to understand to do. There is a work by Xu Heng who has studied the large radius limit of ADS 3. But the limit is it's a very interesting type of limit. You don't look at the Hilbert space on ADS, but you look at a Hilbert space on a circle here and on another circle here. And these two are in global coordinates, pi units apart. And then when you take the limit, this circle goes to sort of this entire region, limits to scri plus, and this entire region limits to scri minus. And so when you now take the limit of the large radius limit, there is no sense of a continuous transformation at any point in time, because I'm sort of always separating scri plus and scri minus with this fixed units of pi. Simply comes from the fact that that's how long a light ray takes to travel from one end to the other end in global coordinates in ADS. And so in this case, this is one way I think that you can try to do large radius limits of ADS CFT, and they have obtained some nice results from there.
And sorry, what were your soft modes in this ADS?
Yeah, good question. No one knows. No one has proper. ADS always has a finite dimensional asymptotic symmetry group, whereas Minkowski spacetime has infinite dimensional. So somehow in the large radius limit, you have to reproduce this infinite dimensional symmetry group, which is just, I don't know where that's going to come from.
But the boundary gravitons don't play a role.
No, well, in ADS3, you could do that. That's the reason actually why Shuhong worked in ADS3, that works. But in higher dimensions, you still have super translation. In 4 dimensions, you have super translations, which is an infinite dimensional symmetry group. But you don't have an infinite dimensional symmetry group for ADS4. But somehow they must show up when you take the large radius limit.
Why can't you have super translations for ADS4?
Oh, super translations is a feature of null boundaries, and ADS just doesn't have a null boundary. The ADS symmetry group, asymptotic symmetry group of ADS is ADS4 is just CFT3, which is a finite dimensional group.
Sorry, Prahar, I missed I thought you were saying that when you put the mu cutoff in flat space, that is somehow working in this ADS space. Please make that statement again. What is the connection between putting the mu cutoff flat space in this ADS space?
It is somehow working in ADS space, but because at least in my work, in this talk that I've told you about, we are discussing with purely the soft modes, right?
Yes.
Just the soft modes.
Yes.
So the translation symmetries act trivially in the soft mode because they have zero energy.
So then it's not the same as working in ADS.
It's not the same if I was to try and generalize it to all the modes in the theory.
Okay.
But if I was trying to study the soft sector, then you can still make this restriction because on the soft sector, the translation group acts trivially. So the effective symmetry group for the soft sector is just the Lorentz group and nothing else, which is finite dimensional. So I have a finite dimensional symmetry group that's acting on the soft sector of the theory.
Okay, thank
you. Okay. So I'm not gonna explain it anymore. But here I wrote down the action just as a function of C. But remember, I had neglected this second soft operator S. And what I told you that I would do was that I would first use symmetries to write down the effective action for C, and then you would integrate in the soft operator mode S. And I'm not going to explain how we do that, but this is what the action looks like, which again, notice is very nice and local in terms of C tilde, in terms of the shadow mode, which is very nice. And
yeah, it's obvious, right? I mean, if you integrate out S, you will get C tilde from this action.
Obvious, completely. And you can check that this indeed reproduces the soft theorems exactly right. So if I compute this endpoint function with some insertions of S and some insertions of U, the U insertions end up giving me the infrared divergent factor, and then the S insertions precisely give me the soft factors. So this action that I've written here in this boxed form reproduces the complete soft sector of the theory, which includes soft exchange and soft theorems. And I should put complete in quotes because I haven't yet told you about the phase of gamma. Okay, so I'm just gonna end it here. I've made all of these comments. I don't think I need to go through any of these anymore. I don't think that I'll just flash. So all of this works exactly for gravity as well, which you can go through. And the effective action for gravity, let me just write it down. It just looks like this. That's the effective action for gravity, where again, these ends are just the soft mode. So limit omega goes to 0 of omega OAB. Remember, graviton transforms in the symmetric traceless representation of SOD. So that's why there are two indices over here, which are symmetric and traceless. And you have the CAB, which is just the boundary mode of the graviton fluctuation. So you remove out the background metric, which is of course flat space-time, and then you study the leading order fluctuation. That's how you define the graviton. So CAB is simply the boundary value of that mode. So again, it's a nice and simple action. And I won't bother going through any of these details. Okay, so a couple of open problems, which I haven't gone through. The first thing is, how does the imaginary part of gamma fit into this? And I'm going to tell you the answer in the next slide. And the second thing is how we can generalize this to non-Abelian theories. And actually, this is indeed the correct generalization to non-Abelian theories. Firstly, it's local in terms of C tilde. which is an interesting fact. But remember, in the case of non-abelian theories, the scattering amplitude does not factorize in such a trivial way. It's a very complicated soft, and there's a whole field of study whose basic job is to try and study the soft collinear effective action, which is not action, soft collinear sort of structure of a scattering amplitude in a non-abelian gauge theory. And we've actually shown that to at least two loop order, that this very simple action reproduces all of those complicated formulas in non-abelian. But the truth is that this action looks very simple. But if you want to do calculations on non-abelian gauge theories, you have to expand this out. And when you expand it out, you get a horribly complicated looking action, including a term that's sort of non-local. And so actually trying to work out the correlation functions in this action is relatively complicated in reality.
What's the analog of a soft gluon?
It's just S. Just this S.
No,
So
I mean, does a soft gluon at all exist?
well, it doesn't exist in nature because of confinement. Yeah. But you can look at QCD and you can add 10 scalar fields, and then you no longer have confinement. So of course, this will apply only in theories in which. So in other words, again, this is a soft action. So the idea is that if a soft set of exists, then the symmetry will constrain that. But if there are no soft modes, then the soft sector is completely trivial, which will happen in a theory with confinement, in which case nothing that I've said applies to any, we don't say anything about confinement, confined theories. But you can just take UCD and add 10 scalar fields, then you have a soft plane.
But what about n equals 4 Yang-Mills? Would there be a non-trivial coupling constant in dependence in this action?
Yeah, that's coming in this alpha, right? Alpha is this coupling constant.
But it's as simple as that. That G Yang-Mills is just.
The problem with one of the issues with Yang-Mills, with n equal to 4 Yang-Mills, is that all particles are massless. So there is a whole bunch of particles in the soft sector, which all of them couple to each other. Here, I'm assuming, for instance, when I write down this formula, I've assumed that the gluons are massless and everything else is massless. So I only have gluon soft modes. But in n equal to 4, I would have to sort of really discuss the gluons, the scalars, and photinos, whatever, gluinos, everything has to be discussed in one whole thing. And so I doubt this simple thing will generalize to that.
But even in QCD, you have massless gluons, right?
Yeah. So in standard QCD, I mean, with nothing else, you don't because of confinement.
So all this doesn't apply?
No, none of this applies. But as I said, you can take QCD with a bunch of other things. Yeah, anyway, I don't want to say anything about confinement. I don't want to make any strong comments. But I have no idea.
Can I ask a question?
Yeah.
Yes. So is the claim that this kind of a structure would completely reproduce something like soft collinear effective theory? Is that what you want?
Well, actually, this yeah, I don't know. I mean, I'm looking at it a little bit, but when I gave this talk at the Celestial Amplitudes workshop, there was a bunch of people from SCET. They found it very interesting. And I know there are some people who are trying to use this action, and I've been told that they've tried and reproduced various structures in SCET up to 2 loops. And not just the soft theorems, but various other features have been reproduced. There are other issues in non-abelian gauge series, which I have completely overlooked in this discussion. In particular, the issue is that here, let me show you. Well, let me just write it here. Is that when I'm trying to compute correlation functions S1 all the way up to Sm, something like this, this seems to be unambiguously defined in gravity and abelian gauge theories. But in non-abelian gauge theories, because the order of soft limits actually is crucial, taking different orders gives you different soft theorems. You have to actually present a definition for what these S1s to Sms are. There has to be some ordering ambiguity that you have to resolve. And this is actually the reason that SCET is so complicated, is because the non-abelian structure really of the soft sector really screws you to an extent. So I'm not totally sure what the actual power of this. It could well be that this is not enough, that you have to add other higher order terms to completely reproduce all the SCET terms. But as what we do know, and what I am sure about, is that whatever it is, it has to be governed by symmetries. So you have to at least make some claims about just use symmetries to constrain the terms. And clearly there's not going to be just one term. You can add a whole bunch of extra terms. And then compute.
So,
So it does indeed apply. I mean, this
think
indeed
it
applies
does.
for.
I think it does, but I cannot. I think it does, but I have not worked on it or done any explicit calculation. So I would be.
But are there any soft theorems for QCD? I don't know.
Yeah, there's soft gluon theorems.
Okay.
Yeah, soft gluon theorems exist. All of these asymptotic symmetries exist. This entire symmetry structure continues to exist, even in the gluon case. The only complication is that these actions are now no longer simple, because now firstly look at the structure of C. C is now U d U inverse, which if I expand it out, this C has the form d theta plus F A B C A theta B d theta C plus so on and so forth. So there's an infinitely many terms in the action, and you have to keep track of all of these infinitely many terms to work out the structure of the action. And so correlation functions take a very complicated form.
So soft photons are something like photons which come from infinity and impinge on the scattering amplitude, right? I mean, you can't have gluons like that.
No, you can. If you have soft gluons,
gluons are necessarily confined, right? I mean,
I'm assuming. I already said none of this applies in a confined theory. So I'm assuming that you have a theory without confinement. So that which you can do.
So what I'm saying is, how does it apply to QCD as S8 or some things like that?
No, nothing. It doesn't.
What then you said that people are applying it to SCET?
Well, you can do. You're still doing SCET is what's just soft. The structure of soft gluons is what they are studying, and that's just coming from various low energy limits of Feynman diagrams. So you can still look at high energy scattering amplitudes where gluons are effectively can be used as external states. And if you can have gluons as external states, then you can have. So in other words, when I say low energy, remember, since energy is a dimension full parameter, I obviously only mean low energy in a ratio. So I mean that the energy of the gluon is much, much smaller than the effective energy of all the other particles. Now I can consider a very high energy scattering amplitude, but all the particles have exceptionally high energy. And then in that scattering amplitude, the gluons, and I can take a gluon to have comparatively low energy. And in that, and even not zero, but still comparatively low energy. And in that limit, that is the regime that the SCET people are studying scattering amplitudes in. So in that limit, the gluon still has low energy with respect to all the other particles in the theory. And indeed, in that case, I believe this structure will continue to hold.
So I think the assumption is that the gluon may be emitted, but then it hadronizes. But
it hadronizes. So we are looking at the regime before hadronization.
Before the hadronization, yeah.
Yeah.
Sorry, Prahar, let me say the thing I find surprising about this. I think you're saying that the coupling constant dependence in this alpha is all in this alpha. So it's all just like one term. So for QED, that sounded very reasonable because there was this exponentiation of one loop.
Yeah.
Is this expected to continue also for non-abelian theories?
No, we don't, because this is a bit of a so let me write it out here. So what's the action? The action that we're roughly saying is 1 over alpha integral trace C tilde what was it, wedge star C tilde, something like that. That's the action. Okay. And where now the C tilde is U d U inverse. Okay. So I'm supposed to expand out this thing in powers of alpha. So what I'm supposed to do is I'm supposed to write U, because I have to give the kinetic term a canonical scale. So I need to write U is equal to e to the square root alpha times phi or times theta, if I want to use the same notation. In which case we find that C tilde, if I plug in all of this, is precisely equal to alpha d theta. Let's put in a Lie algebra group index alpha. Then there's a alpha to the 3/2 f ABC theta b d theta c, plus there's an alpha square term, and so on and so forth. And now I plug this back into my action. So my action, when I want to compute actual quantities in an effective expansion in alpha, contains lots of terms. Contains the leading order term will of course just be the propagator. So it'll just be 1/2 d theta squared, but then there'll be a term which is order alpha. What is it going to be? Alpha to the 1/2, something like this, with the f ABC, theta A, d theta B, d theta C, and so on and so forth. So it's just a nonlinear sigma model with a non-abelian target space, and you have this whole expansion in alpha. So it's now no longer going to be just a trivial thing. You'll get a very complicated alpha dependence.
Right, but you say that the entire thing comes from one classical action with one coupling constant dependence, and then expanding that in nonlinear.
That's what this analysis suggests, but and I have not done any calculation to be absolutely certain of that. But it does.
You could imagine that there's new structures at each order, right?
You could imagine. That's what I'm saying. But I think even if there are new structures, they're going to be governed by symmetries.
Okay.
So, and I think the issue is that because alpha is dimension 4, so if I include any extra factors of alpha, that also corresponds to including extra derivatives acting on C. And derivatives acting on C is extra factors of omega, so they might be subleading in the omega expansion, which is fine because the actual sket amplitude includes a full omega expansion. The sket so if you want to reproduce just the leading order term in the sket discussion, I do think that this first term is enough.
I see.
But
it's like Einstein gravity is leading order in the alpha prime expansion, but there's a whole series.
There's a whole series, yeah, and there are probably other terms you can write down, which will you have to keep track of alpha to alpha.
Thank you.
Okay, another thing is this C is UDU, so shadow C is not UDU, right?
I'm being very lax over here, but you're absolutely right. You're absolutely right. I should have written this, and then now this will also be non-local. So when I plug it all in, it's like shadow of all of these things.
Yeah.
Shadow C is that, and so now the action is actually very non-local when you write it out at the end of this. I'm obviously being very, very lax in this, and I shouldn't be, but I hope you understand. Basically, my point is that it's clearly very complicated, and this is one of the reasons why. But if this can be shown to be true, I would be really interested in. It would be very nice because we already know that sket is very complicated. There's a reason. There's a whole field that studies this. But it would be interesting to see if all of that complication really boils down to the existence of this type of very simple shadow non-locality.
Somehow the point is that there is a locality in this effective action, right? In these variables, in the new variables.
Yeah.
And that would allow you a simple, parameterization in the omega expansion.
Yeah.
So I think understanding this locality would be useful.
Yeah. Yeah. What I know is that to leading order up to 2 loops, it's been checked that this actually works. But I also don't think that's a very strong check. I kind of feel like that had to work out because of anyways, I don't think I do know that I was contacted by someone who has sort of used this action to try and work out the 2-loop correction to the leading order sket factorization, and it ended up matching, which is great. But I have a suspicion that that's something that had to match in some sense. So it's not really a non-trivial check as of yet. But anyway, as I said, that's why this is in my comments, is that this is a conjecture. I've mentioned it clear. We conjecture that this is actually the action that will probably give us the right answer based on symmetry arguments. And it would be interesting to explore this and see if this is right.
Are you finished, Prahar?
Yeah, but I wanted to just show you the imaginary part of gamma, which is this. I don't really have much to say beyond it. The point is that this is the structure for the imaginary part of gamma. Firstly, it has it sort of crucially distinguishes between in and out states separately, which A1 did not do. And then here's the action, which again, simply by construction. Unfortunately, here I do not use any symmetry principle, just based on what we already know. I just constructed an action by hand that gives us the right answer. But I have no reason to understand. I have no explanation for why this is correct. But another interesting thing about this action is that there are a whole bunch of other soft theorems that I discussed that I did not discuss, even for just soft photons. There are these things called simultaneous soft limits, in which, so when I inserted S1, S2, S3, S4, these multiple photons, I was taking each photon to be soft one at a time. And because they were photons and photons are abelian, the order in which I take them to be soft turns out to not matter. So all the soft theorems that I've discussed so far are the soft theorems corresponding to what's called consecutive soft limits. You take limits one at a time, but there are also simultaneous soft limits, which have a whole different structure. There's also, it's still a factorization, but the corresponding soft factor is much more complicated. And it's also only there in non-Abelian gauge series, by the way. It's not a structure that you can find in Abelian gauge series. And surprisingly, the same action that reproduces the imaginary part of J somehow also reproduces the simultaneous soft theorem. So I think this is the correct answer. I don't know why. It's just something I constructed by hand so that it matches everything. But as as you should notice that I did not have to do this previously, but now I have to make a crucial distinction between in and out states. They have to be separately treated. And so as I have discussed this before, this is a problem, or perhaps an interesting feature with respect to crossing symmetry. When I take an in particle and move it to an out particle, then the structure of this soft action actually changes as well. So that's just so anyway, I'm done. I'm sorry, I really took a lot of time.
So this S soft that you have written here,
yeah,
it reproduces just the A2 or the full action?
Let us first thank Prahar for a wonderful talk, and then we'll continue with some questions.
Thank you.
Yes, a few questions because it must be very, very late. And we have already had many questions. So just urgent questions, a couple of them, please.
Yeah, so what I was saying that this S soft it reproduces the it corresponds to the imaginary part of gamma A2 or the full action?
Just A2. So if you want to reproduce the full thing, you have to include the soft action that I discussed in the main part of this talk, plus all of this extra piece. And so together, the what I discussed then plus this will reproduce all of gamma, the real part and the imaginary.
So that's some calculation that you still have to check, right?
No, that part of the calculation is checked. The reason I haven't written it out is because I don't have an explanation for this, and I don't want to have a paper in which I just write down something without any actual motivation or I just literally wrote it out because it's, well, based on previous results. Firstly, we knew it was local with respect to the shadow mode, and it was quadratic. So I just made a guess that, well, let's just try and write down something that's quadratic and local with respect to the shadow mode. What is clear that I had to introduce two modes. Well, I had to actually introduce it infinitely many modes because the structure of A2 is such that you have two modes. You have two pieces inside here. One of them involving just the in states and another one involving just the out states. So notice that there is no mixing between in and out states. So this is a very interesting type of structure. And then all of this, there's an extra dependence on this parameter nu, which was not there at all. So if you want to reproduce this type of quadratic structure, it's very clear that in order to reproduce this structure, I need to introduce a field C plus, which now depends on nu in addition to its dependence on X. And then in order to reproduce this, I need to have a C minus in addition to depending on X. And these fields now have to be complex because each of these J's are complex, unlike earlier when they were all real. So just by hand, you can write down this action and it works.
Yeah, but just as you could derive it for the other case, can't you derive it here as well?
Well, I don't have any symmetry arguments. The point is that I don't yet even understand what these fields are and how they should be related to the boundary modes of the gauge fields. How does the symmetry act on them? I have some idea now, but I don't think I have anything sufficiently concrete to make any claims. But the point is to try and understand what are the symmetry transformations? How do they transform under the action of symmetries? What is the large gauge transform of these guys?
So what did you check the action against?
Well, just this. You take S soft and you evaluate the path integral, and you get this. You reproduce A2. That's literally the extent of the calculation, which is as trivial as you can be. Which you can just see. Look, you can stare at it and tell, and you can see that it's the right answer because it's just a Gaussian action.
Yeah, you integrate out the C and you get A2.
Yeah,
right? That's what.
So you could just say this is obviously trivial. Like and that's kind of one of my points is that because it's just something you write down and it's the most obvious guess. and there is no motivation behind it. So the first step would be to try and understand what is the correct motivation behind it. But I do think it's the right answer, because completely separately, unrelated to this thing, as far as I understand, is that it also reproduces simultaneous soft limits, which in my opinion, it had no right to. It had no right to reproduce simultaneous soft limits.
But I think one problem would be that if you included A1 and A2 together,
Yeah.
integrating out C1, C plus and C minus might not work in the most easy fashion.
No, but they don't talk to each other. C plus, C minus, and C are all totally independent fields.
Okay, then it will work.
They don't talk to each
I
other.
thought C plus and C minus were in and out fields of C.
No, that's what I'm saying. They're not. They're just independent. That's why I don't have any actual space-time intuition for what these fields are as of now.
But J plus minus are in and out fields of J, right?
Sort of. But remember, they have an extra new dependence. So they're just not in and out. The J that I defined previously and everything that I defined previously depends only on X. There was no extra new dependence. Here, there's an extra integral over nu, which was not there in the case A1 was simply equal to integral d dx curly J of X squared.
Can't you absorb these factors into phases of the external states rather than interpret it as an action contribution?
No, you cannot. You cannot. You cannot, because they're not sum over this. There is a pairing. So this out coupling goes in here, and there's an in coupling goes in here. So it's not like they're independent phases for each particle, in which case I could absorb them. But there's a whole, because this is squared, remember, and I'm summing over in squared. So there's actually a interaction between pairs of in particles and pairs of out particles. So this cannot just be removed by a phase redefinition.
Prahar, can I make a comment on your like A1 and A2 factors from our work? Like
Loga has a question. Loga had raised his hand, but maybe if Loga can postpone, you can go ahead.
Okay, sorry. Just okay. Should I continue?
Yeah. Maybe I think I was probably going to say what Viswajit is saying, so maybe I'll just let Viswajit ask the question. Yeah.
Okay, like the comment I wanted to make is that like this A1 and A2, if you see, like they have a like physical like understanding. The thing is that this A1 is basically which you defined as the imaginary part of this gamma. So this is like basically this, like basically cancels with the like in the like if you compute a inclusive cross section, this A1 part actually exactly cancels to the part when there will be like real soft photon emissions.
Yes.
And this A1 is basically this is the factor, and A2, if you make mod square of this like when you compute cross section, you take modulus of the amplitude, A2 will go away. But this A2 is actually the physical, like the long range force effect, and which you will see like if you compute say gauge field like in classical computations or even in the soft factor computations when this soft, like the tree-level soft factors operating on this gamma. This A2 is basically the physical part which contributes to these memories or even like the tail memories. This is the part which it contributes, and it is related to the fact that the long-range interactions. And it is also it is also obvious from the causality that only in particles have long-range interactions and out, not between in and out states. So yeah, so this is like the physical intuition we have for the A1 and A2, and yeah, I don't know whether it helps, but just to make a comment.
Yeah, I agree. I mean, the fact that it's physical, I think, answers also the previous question that it cannot be removed by simply redefining the phases of all the in and out particles. Yeah, thank you.
Okay. Are there any more questions? Comments? Okay, if not, let's thank Prahar again for a very nice talk.
Thank you.
Thanks a lot, Prahar.
Yeah, thank you.